This is lecture second of the continuous mass distribution and the lecture code is CCD02. First of all, you can write the lecture code CCD02. Okay. Now see, in the first lecture we have seen what is the meaning of continuous mass distribution, that is some extended object with a size. We have seen the concept of infinitesimal element. Any extended object can be assumed to be made up of a large number of infinitesimal elements, and each infinitesimal element is continuous in nature and each element can be treated as a particle. Then we have seen the meaning of mass density, which is the mass contained in unit element, and there are three types of mass density: linear mass density, surface mass density, volume mass density. And mass density is a microscopic property, that is property of a point in an object. It may vary from one point to another point in the same object, correct? Now in this lecture we will start with the concept of linear mass density. Linear mass density, denoted by the Greek alphabet lambda. Okay, so we are starting with the concept of linear mass density, which is denoted by the Greek alphabet lambda. Now see, linear mass density is the mass contained in unit length. Okay, linear mass density is the mass contained in unit length. And when we use the concept of linear mass density, when the mass is distributed along any length. When we use the concept of linear mass density, when the mass is distributed along any length. Okay, so we use the concept of linear mass density when the mass is distributed along any length or line. Okay, so this is how we use the concept of linear mass density. Now this length over which the mass is distributed can be straight, rectilinear or curvilinear. It can be straight, rectilinear or curvilinear. Okay, so the length can be straight or the length can be curvilinear. So we can have the mass on a straight or rectilinear line, or we can have mass on a curvilinear line. Got it? Now let's see how we define the linear mass density, since it is the property of a point. So say we have some segment of line. This is some segment of line, okay? And in the previous lecture we have seen at any point we can take a particle in the form of infinitesimal element. So suppose you have to find the mass density, linear mass density at a point P. So at a point P I am taking an infinitesimal element, say of length dx with a mass dm. Okay, now see, there is a skill of calculus when we divide two quantities, both are infinitesimal. Suppose I am writing an equation, a is equal to b divided by c. Now in this case b and c are finite quantities. Now if you take b and c in extremely small amount, when we say we are taking b and c in very extremely small amount, it means infinitesimal amount. So instead of b we will write db and instead of c we will write dc. So it is the division of two infinitesimal, correct? It is basically the division of two infinitesimal. So answer will be a finite quantity a. So when you divide two infinitesimal, the answer comes to be a finite quantity, remember. Okay, so if you're writing something like velocity is equal to displacement by time. So these are the division of two finite quantity. If instead of s you take ds, instead of t you take dt, so it's the division of two infinitesimal quantities. So answer will still be a finite quantity v. Answer will be a finite quantity v. Okay. So whenever you divide two infinitesimal quantity, always remember the answer is always a finite quantity. Rule number 1. Okay. Now rule number 2 is, suppose we have multiplication of two quantity. Say a is equal to b into c. So b is a finite quantity, c is a finite quantity. But suppose in place of c you are taking infinitely small c, say dc, that is infinitesimal c. So you are multiplying a finite quantity with infinitesimal quantity. You are multiplying a finite quantity with infinitesimal. So answer will be infinitesimal. So in this case, instead of a, the answer will be written as dA. Okay. So these are the two rules. When you divide two infinitesimal quantities, the answer is always a finite quantity. When you multiply a finite quantity with infinitesimal quantity, the answer is always an infinitesimal quantity. Okay. Right. When you write work, so work done by a constant force is force dot displacement. This is the formula. Now if in place of s you take infinitesimal displacement ds, so work will be F dot ds. Now this will be written like dw, because a finite quantity is being multiplied with infinitesimal quantity. That's all the notations of calculus. Got it? So when I'm talking about the linear mass density, so I'm saying in this case I have to find the linear mass density at a point P. So I've taken an element, an infinitesimal element of length dx and mass dm. Now I'm making a highly magnified figure of this element, so it will look like a slice. It will look something like a slice like this, of length dx and of mass dm. So at this point we have to find the value of lambda, correct? We have, our target was to finding lambda at this point. So at this point lambda will be the mass contained per unit length, that is dm by dl. So this is the defining equation of the linear mass density at any point. At which point you have to find a linear mass density, take some element, infinitesimal element of length dx and its mass dm. So lambda at that point will be dm by dl, dm by dl. So here you can see the unit of lambda, unit of linear mass density will be what? The unit of mass is kg and the unit of length is meter. So the unit of lambda will be kg per meter. That is the SI unit of linear mass density. Got it? So this is the defining equation of lambda dm by dl. Okay. Now let's see. Suppose I have some segment which has a total length L, and I am taking some element, I am taking an infinitesimal element like this. From this the linear variable is x. In the last lecture we have seen how to run the linear variable, and the width is dx and the mass is dm, and at this point lambda is lambda. So we have seen lambda is equal to dm by dx. So therefore dm will be what? Lambda dx, correct? So if you have any element whose length is dx and linear mass density is lambda, you can write its mass as lambda dx. Now in the complete length, suppose this is a thread, so in the complete length, in the complete thread, there will be very large number of such elements, correct? Already we have seen in lecture 1, any extended line, extended object can be assumed to be made up of a large number of infinitesimal elements in a continuous manner. So there will be a large number of such elements, each will contribute some mass dm. Now if I have to find the total mass of this white thread, if I have to find the total mass of the white thread, total mass of thread, say m. So for finding the total mass, we have to add up all dm, correct? You have to add up all dm. You have to add up the masses of each element. And in the language of calculus, when you add up infinitesimal quantities, dm is an infinitesimal quantities. So we know in calculus, adding up or summing up means integral. So it will be integral of dm. This is the total mass. So m will come to be integral of lambda dx. So this is how you can find the total mass. M is equal to lambda dx. Now the point is, what you think, whether lambda will come out or not, and you have to put the limits of x. So since the rod has a total length L, so x will begin from 0, as we seen in the last lecture how to put the limits, and x will run till L. Now question is whether lambda will come out of the integral or not. Now it depends. In the first lecture we have seen precisely density is the microscopic property. It means it may vary from one point to another on the same object. So lambda may vary from one point to another on the same object. So it is not necessary that lambda will come out of the integral, because lambda will come out only if it is constant. In a very special case, when you say the object is homogeneous, when we say the object is homogeneous, that is mass is uniformly distributed, this is what we have seen in lecture 1, then lambda would be what? Lambda would be constant in this special case. When the object is homogeneous, then lambda will be constant. So in this case, lambda will come out of the integral and you will have dx from 0 to L. So it will be lambda x from 0 to L. So m will come to be lambda L. So this equation has a limited application. This equation has a limited application for homogeneous object. Okay, and in homogeneous object, if you make lambda, it will be total mass by total length. But if the object is not homogeneous, or if we don't know what is the nature of the object, so we will apply this equation. M is equal to integral of dm, and dm is equal to lambda dx. Okay, so this is a limited equation. When we apply this equation, when the object is homogeneous, correct? So you can still the video and note all these things and the special case for homogeneous object. Now we will see some of the illustrations which will make all these equations and applications of these equations more clear. To see illustration 1. Suppose we have a rod. Okay, we have some rod and it is given the rod is homogeneous, that is the mass is uniformly distributed, and the rod has a length L and mass M. Okay, now see, since the rod is homogeneous, so if you need to find lambda for the rod, you can apply total mass by total length. So lambda for the rod will come to be m by L, simply m by L, it's homogeneous, and lambda will be same on the complete rod. Now suppose if you are taking some segment of the rod, suppose you are taking this much segment of length L dash. So you got a segment of the same rod, and the length is L dash, and let's just mass be m dash. Now what will be m dash? Since lambda will be same, don't write lambda as lambda dash, lambda will be same as rod is homogeneous. So m dash you can write as lambda into L dash, correct? The mass of this segment will be lambda of the rod, multiplied by length of this segment. So m dash will come to be, put the value of lambda, m divided by L into L dash. This will be the value of m dash. So this is the first application. How you can find lambda, for a uniformly distributed rod or homogeneous rod, and then how you can find the mass of any segment on the rod. You can apply this formula or this formula, lambda is m by L or m is lambda L when the body is homogeneous. Now see the second illustration. Suppose I have a rod and the rod has 3 different segments. Okay, this length is L1, this length is L2, this length is L3, and in this segment linear mass density is lambda 1, this segment has a linear mass density lambda 2, and this segment has a linear mass density lambda 3. So if you see, the complete rod has variable lambda. The complete rod has variable lambda, but there is one point. Lambda is not changing from one point to another point. Lambda is changing in segments. Something is changing in segments. So we need not to use calculus. Lambda is changing in finite segment. Calculus will come into play when something will change continuously, when something will change from one point to another point. So in this case, lambda is changing in finite length. So you can find, say it has a mass m1, this segment has a mass m2, and this segment has a mass m3. Now we can say the whole rod is non-homogeneous, but each segment of the rod is individually homogeneous. So you can apply the homogeneous equation for each segment. So your m1 will come to be lambda 1 L1, m2 will come to be lambda 2 L2, m3 will come to be lambda 3 L3, and the total mass of the rod would be m1 plus m2 plus m3. There is no need for integral since we are not using any calculus. So m will come to be lambda 1 L1 plus lambda 2 L2 plus lambda 3 L3. This will be your final answer. Okay, this will be the answer for this problem. Got it? So this is your second illustration. Okay, so this is how you can find mass of the individual segments and then add up all the 3 masses. Now let's see illustration 3. Now suppose you have a ring and the ring has a radius r and the total mass is capital M. And again I am saying the ring is homogeneous. So since the ring is homogeneous, and you can see on the ring, you can call it a ring, the hoop, or the loop. So since the ring is homogeneous, that is, the mass is uniformly distributed, and what do you think, how the mass is configured, how the mass is arranged, how the mass is distributed? It is along the length. If you cut the ring, you will get a straight line. If you stretch the portion, when you cut the ring, you will get a straight line. So the mass is distributed on the length. On the ring, the mass is distributed on the length. So if you want to use the mass density, we will use the linear mass density, lambda. If you want to use the mass density, it will be the linear mass density because the mass is distributed over the length. And lambda will be, since it is homogeneous, so we can write total mass by total length. Now what do you think is the total length? What do you think in this case is the total length over which the mass is distributed? So that will be the circumference. So it will be m divided by 2 pi r. Correct? It will be lambda will be m divided by 2 pi r. Now suppose now you are taking any element on the ring. Okay, this is the mass element on the ring, say of length dl and mass dm. So you can say dm, what will be the mass of this element? So you'll say lambda into dl, correct? Dm will be lambda into dl. And if you put the value of lambda, so lambda you can put what? M divided by 2 pi r multiplied by dl. Got it? So this is how we can find lambda for a complete homogeneous ring. Had it been a semicircular ring, so what do you think, what would be the value of L? Had it been a semicircular ring, then L would be pi r, half of the circumference, simple. Okay, so this is illustration 3. Now let's see the cases where we have variable lambda. Till now we have seen the cases where lambda was changing either in finite segments or lambda was constant over the whole rod or length. Now see this illustration. Say illustration 1 for this article, variable lambda. Suppose we have a rod on the x-axis. Okay, we have a rod on the x-axis. This is origin, this is y-axis, and this is x-axis, and the length of the rod is L, and you are given the value of lambda as 2x plus 5 kg per meter when x is between 0 and L, and lambda is equal to 0 when x is greater than L. See, what is the meaning of this inequality? This is your rod, correct? This is the rod. So it is obvious that the mass is present in the range of x when x is between 0 and L. There is no mass when x is less than 0, and there is no mass when x is greater than L. So we can write there is no mass means lambda is equal to 0. Lambda is equal to 0 when x is greater than L, and lambda is equal to 0 when x is less than 0. These are the segments with no mass. Lambda is non-zero, 2x plus 5 when x is between 0 and L. So this is the meaning of these inequalities. Even the inequality is not given. We will assume that lambda will be present only on the segment of the rod. But in problem, sometimes you are given inequalities like this. Okay, and we have to find the total mass of the rod. What is the goal? Find the total mass of the rod. So see what will happen. In this case, lambda is given as a function of x. The first key point is lambda depends on x, and x is the coordinate of the point. X is the coordinate of the point on the rod. So x is changing continuously, correct? X is changing continuously. So x is basically the coordinate of point which will change continuously from one point to another point on the rod. It implies that since lambda depends on x, lambda is changing continuously on the rod, and we know when something change continuously from one point to another point, then we have to use calculus. So this is the case where the body is non-homogeneous and lambda is changing continuously from one point to another point. This is giving you the trigger, this is giving you the hint for using the calculus skill. Always remember, you have to think which information in the problem is giving you the hint for employing the skills of calculus. So in this case, there is something which is giving you the hint that you need to employ calculus, because lambda is a function of x, and x is changing continuously on the rod, so lambda will change continuously. So we cannot apply that equation m is equal to lambda L in this case. We cannot apply that equation m is equal to lambda L in this case. So what we will do, we will take an element we will take one element like this. So I'm taking this element, okay, say I'm taking the running variable from this point as x, and if I'm taking the running variable as x, in the first lecture we have seen the thickness will be taken dx, and let's its mass be dm, mass of this element. So we know right now we have seen dm will be lambda dx, correct? So this is the mass of this element. Now there will be a large number of such elements, so the total mass of the rod will be integral of dm, that is integral of lambda dx, correct? Now what do you think? What do you think, will lambda will come out of the integral in this case? What do you think, will lambda will come out of the integral in this case? No, exactly, lambda will not come out, because lambda depends on x. Lambda depends on x. So lambda is a variable, it can come out only if lambda is constant. So lambda will not come out of the integral. Now we know the basic rule of integral. If lambda can't come out of the integral, then for doing the integral, lambda must be a function of x, otherwise there will be a blockage. Lambda must be a function of x, and that function of x you are provided in the problem, 2x plus 5. You are given in the problem lambda is 2x plus 5. To put that value of lambda, so you'll get 2x plus 5 dx. Now put the limits of x. So we know the concept of the running variable as seen in lecture 1. X is starting from this element. So for and x is starting from the origin. So for this first element, x will be 0. For this element, x will be 0, and for the last element, x will be L. So put the limit. So when you are putting the limit, so you will put the limit of x beginning with a value of 0 and x running till a value of L. So m will be, the integral of 2x will be 2x square by 2 plus 5x within the limits 0 to L, you will get cancelled 2. Now put the limit, you will get L square plus 5L minus 0 square plus 5 times of 0. So the second term will be 0, and you will get the answer as the mass will come to be L square plus 5L. This will be your final answer. Okay, this is a final answer, the total mass of the rod. So in this illustration we have seen, a case where lambda is changing from one point to another point, and for such cases we will take the element and we will write dm as lambda dx, and then we will integrate dm to get the total mass, and in such integral lambda will not come out of the integral. Okay, now let's move to the next illustration, illustration 2. So suppose again I am saying I have a rod on the x axis, so this is the rod on the x axis, and so the rod is kept between x is equal to a and x is equal to 3a, and the lambda on the rod is given as lambda naught x square kg per meter. This is the value of lambda. Lambda naught is some constant. Lambda is given on the rod as lambda naught x square. Lambda naught is some constant, and we have to find the total mass of the rod. Find the total mass of the rod. So again you can see lambda is a function of x, like in the previous illustration. Again you can see lambda is a function of x. So if lambda is a function of x, and x will change continuously on the rod, so lambda will also change continuously on the rod. So we cannot use homogeneous equation. Instead, we have to use calculus. So we'll take a mass element. So I'm taking this as the mass element, and I'm taking the distance, the x coordinate, as x from the origin, and the thickness dx, and the mass dm. So this mass element, we can write dm as what? Lambda dx, and there will be a large number of such mass elements. So the total mass of the rod we know will be the integral of dm, that is integral of lambda dx. Then now again the same question, whether lambda will come out of the integral or not. What do you think? Yeah, lambda will not come out because lambda depends on x. Lambda depends on x. So lambda is given to be lambda naught x square. So put this value of lambda in this equation, lambda will not come out, so we'll get lambda naught x square dx. Now lambda naught can be taken out because lambda naught is a constant. So m will come to be lambda naught x square dx. Now the integral is possible. The integrand is a function of x and the variable is also x. So put the value of x. X begins with, now see where the rod is beginning from. So if you see the figure, the rod is not beginning from the origin. The starting of the rod is at x is equal to a. So the first element of rod will have a limit x is equal to a, and the last element where the rod is ending has a linear variable limit x is equal to 3a. So the limits of x is from a to 3a. So I'll get lambda naught is a constant. The integral of x square will be x cubed by 3. Now put the limit a to 3a. So mass will come to be lambda naught by 3. In place of x put 3a cube, minus in place of x put a cube. So what I will get? We'll get a cube common. So mass will come to be lambda naught by 3 a cube. 3 cube will be 27, minus 1 cube will be 1. So I'll get 26 by 3 lambda naught a cube. This will come to be the mass of the rod. So this is the answer for this problem. Got it? So this is the second illustration where we have seen how we will approach when lambda is changing, how we will approach when lambda is changing with x. Okay, when lambda is changing with x, then what will be the approach? Got it? Now let's move to next illustration. Now see illustration 3. Suppose again we have some rod on the x-axis. Okay, so we have some rod on the x-axis. So this is a rod, and this is O, and this is x is equal to L. The length of the rod is L. And you know you are not given the mathematical equation, but instead you are given a function how lambda is changing on the rod. So you are given the variation of lambda on the rod is like by this graph. This is the graph of lambda, and this is x, and this is L, and this is lambda naught. So this is the variation of lambda with length, or x, variation of lambda with x. And the problem says find the total mass of the rod. Find the total mass of the rod. So say again, you can see first of all in the previous two illustrations lambda was given a mathematical function of x. In the previous two illustrations lambda was given a mathematical function of x. In the present illustration lambda is not directly given as a mathematical function of x, but instead the representation is given by the graphical view. lambda is given as a graph of x. So the first skill will be, from the graph, get lambda as a function of x. Skill 1 will be, from the graph, get the equation lambda as a function of x, and then you will simply follow the skill of the previous problem. This is something which is the first skill in this case. So we can see it's a straight line graph. The graph is something like this. So it's a straight line graph. So straight line graph has a basic equation we have seen in the mathematical tools. Y is equal to mx plus c. M is the slope and c is the vertical intercept. In this case, in place of y, we have lambda. Okay, the dependent variable is lambda. So lambda is playing the role of y. In place of x, we have x. On the horizontal, we have x. So x is simply x. We have to transform. This is the prototype model equation. You have to compare what are the present variable. So in this problem, in place of y, we have lambda. In place of x, we have x. Now let's find the slope. So slope is your rise by run, and the graph is coming down. The slope will have a negative sign. So it will be minus lambda naught by L, and the intercept will be lambda naught. So your function will come to be, in place of y put lambda, in place of m put lambda naught by L, x plus lambda naught. So this is the first skill. You got the function, mathematical function of lambda in terms of x from the graph. This is the first skill. You got the mathematical function of lambda in terms of x from the graph. And again you see, since lambda depends on x, so now it's like the approach of the previous two illustrations. Lambda depends on x, so lambda is variable for each point, and since lambda is variable for each point, so we have to use calculus. So now the problem is very straightforward. This is your rod. Take one element at a distance x, thickness dx, and say this element has a mass dm. So dm will be lambda dx, and m will be total mass of the rod, integral of dm. So it is integral of lambda dx, and again we can't bring lambda outside because in this case lambda is a function of x. So we can't bring lambda outside, and we have to put lambda as a function of x, then only the integral will be possible. So we'll get minus lambda naught L x plus lambda naught dx, correct? So you will get, and you will put the limit of x is beginning with 0 and running till L. So now this is constant, lambda naught and L are constant, so it will remain the same. The integral of x will be x square by 2 plus lambda naught is a constant, and the integral will be x. Like for a, the integral is ax, 5 integral is 5x. So for lambda naught, integral is lambda naught x. Put the limit 0 to L. So you will get m is equal to minus lambda naught by 2L L square plus lambda naught L bracket minus lambda naught 2L multiplied by 0 square plus lambda naught multiplied by 0. So this whole term will be 0. So your answer will be, this one L will get cancelled away. So you will get m as minus lambda naught L by 2 plus lambda naught L. So your answer will become to be, this is minus half and plus 1. So m will come to be lambda naught L by 2. This is your answer, the mass of the rod. Okay. So this problem was again for variable lambda, when lambda is changing for each point x. But in this case, in the very first place, you are not given the mathematical function of lambda. You are not given the mathematical function of lambda. Instead, lambda was represented as a graphical visualization as a function of x. So first of all, you have to apply the mathematical skill to transform the graphical view in the mathematical equation. Got it? Okay, now let's move ahead. Now see some skill we have seen in calculus. If you're writing integral of sine 2x dx, your answer will be minus cos 2x by 2. We have to divide by 2. This we have learned in calculus. Cos 2x dx will be sine 2x by 2. And then we have seen some basic trigonometric formulae like cos square theta. I'm just writing the formula, so right now let's not write the integral. When you're writing cos square theta, so you can write as one plus cos 2 theta by 2. And when you're writing sine square theta, so you can write as 1 minus cos 2 theta by 2. We have done all these things in mathematical tool. Right now just I'm making a recap for those who might have not done it. So see, when you are integrating cos square theta d theta, okay, so what you can write, you can use this formula. So it will be 1 plus cos 2 theta by 2 d theta, correct? We are simply using the basic trigonometric formula. Now this will be 2 is a constant, it will come out, it will be 1 plus cos 2 theta d theta. Of course we'll put the limit of theta, so it will be half. Now what is the integral of 1? So the integral of 1 with respect to theta will be theta. And what is the integral of cos 2 theta? So we'll write sine 2 theta, right now we have seen, by 2, and you will put the limits from theta 1 to theta 2. So these are the basic skills which will be applicable in the next problem. That's why I made a little recap of the mathematical tools what we have done here. Okay, now see the next problem. Now suppose we have a semicircular ring. Okay, say of radius r, and you are given this is the angular position of a point. You can also call it as the azimuthal angle, we have seen in lecture 1. So this is a point P, and its angular position from this reference line is say theta. And you're given lambda on the ring, because again the mass is distributed on the ring, so we'll use lambda. I guess this is illustration 4 or 5, whatever it may be, write it down. So lambda is given as lambda naught cos square theta. So you can see in this problem lambda is given as a function of theta. Okay, you can see lambda is a function of theta, and theta will change for each point. Remember lecture 1, theta is the angular variable and this is the reference line. So for this point we start theta from the reference line as we have seen in lecture 1. For this point theta will be 0. For this point theta will be pi by 2, 90 degree, and for the end point theta will be pi, that is 180 degree or pi radian. So theta is continuously changing on the ring. Semicircular ring has a variable theta from one point to another point. So lambda is variable on each point. Lambda is variable for each point. And again something is changing continuously. Remember, so if something is changing continuously on the length, lambda is changing continuously on the length, so we are bound to apply calculus. We cannot use the homogeneous equation like in the previous illustration. The difference in the previous illustration and this illustration is that in the previous 2 or 3 illustrations we were seeing lambda as a function of x, linear variable. In the present illustration we are exploring a problem in which lambda is a function of angular variable. So we will take an element on the ring using the skills we have seen in lecture number 1. So I am taking an infinitesimal element. So say, you remember how to take the infinitesimal element? We'll take something like this, an element of some angular position and some angular width. So from this is the, because theta is given from this line, so this is the angular position theta, and this will be the angular width d theta. Remember, if you are taking this as phi, then this would be d phi. If this is alpha, this will be d alpha. If this is theta, this will be d theta. And say the linear variable, this is L and this is your dl, and this is your element. This is your element which has a mass dm. This is the skill. We have seen how we run the angular variable and the linear variable, and this is a circular, semicircular arc. So we can write dm as lambda multiplied by length of the element. That is the basic equation. Dm is equal to lambda multiplied by length of the element. What is the length of the element? Dl. So it will be lambda dl. Now the total mass of the semicircular ring will be summation of dm, as we have seen previously. Summation means integral. That is integral of lambda dl. Now again the point is, what do you think? Whether lambda will come out of the integral or not? In this case, what do you think? Whether lambda will come out of the integral or not? Think and answer. For that you have to check whether lambda is changing with x or L or not. So lambda is changing with theta. Lambda is given as lambda naught cos square theta. Lambda naught is a constant. Lambda naught is some constant. So lambda is a function of theta. So lambda is continuously changing. So lambda will not come out of the integral. Instead, you have to put the value of lambda as given in the problem. So it is lambda naught cos square theta dl. Now can I bring lambda naught outside? Yes, lambda naught can be taken as constant. So what is left is cos square theta dl from theta 1 to theta 2. Now you have to integrate this thing. But the problem is the integrand is a function of theta, and the variable of integration, that is the variable with d, it is the variable of integration is L. So the homogeneity is lacking. We can't integrate. Either it must be a function of L with dl, or either it must be a function of theta with d theta. So you have to get it in a homogeneous way. So we have seen in lecture 1, whenever we have a circular arc, so we have seen in lecture 1, the arc length is equal to radius multiplied by the angular width. The radius multiplied by the angular width. So what we can write, since it is a circular arc, so we can apply this equation, dl is equal to r d theta. So you'll get m is equal to lambda naught cos square theta r d theta from theta 1 to theta 2. Now r being the radius, it is constant for each point. So it implies that m is equal to lambda naught, r will also come out, and what is left is cos square theta d theta from theta 1 to theta 2. Now let's see the limit of theta, and we know, we have learned how to find the limit of theta in lecture 1. So theta is beginning from this reference line. So we have seen for this point theta will be 0, correct? Theta will be 0, theta will be pi by 2, theta will be pi. When you will come to this side, you will be revolving by an angle of pi, 180 degree. So the first element of the semicircular ring will have theta 0, and the last element will have theta as pi. So put the value of theta 0 to pi. Now we have to integrate cos square theta, and right now I've taught you, you can rewrite this formula, 1 plus cos 2 theta by 2 d theta from 0 to pi. So it will be, now 2 will be outside, so lambda naught r by 2 1 plus cos 2 theta from 0 to pi. So you will get m is equal to lambda naught r by 2, the integral of 1 will be theta, plus cos 2 theta will have an integral of sin 2 theta by 2 within the limits 0 to pi. Now put the value, it implies that m is equal to lambda naught r by 2. Now I'm putting a bracket, instead of theta put pi, so pi plus sine 2 pi by 2 minus, put the value of theta as 0, 0 plus sine 0 by 2, correct? Now you see the basic of trigonometry, whenever we have any integral multiple of pi, sine n pi, n belongs to integer like sine pi, sine 2 pi, sine 3 pi, it will be 0 value, it will have a value of 0, sine n pi. So in this case we have sine 2 pi, so sine 2 pi is an integral multiple of pi, so it will be 0, and this is 0, sine 0 is also 0, so your m will come to be lambda naught r pi by 2. So this is your answer for the mass of the semicircular ring. So in this illustration we have seen how we will approach when lambda is given as a function of some angular variable. Then also we'll take the element, and we'll write dm is equal to same thing, lambda dl, and we'll put the value of lambda, and if it's a circular segment, so in place of dl you can write r d theta. So this is all about your linear mass density. Now in the next lecture we will start with, that is CCD03, we will start with the surface mass density sigma, where the mass is distributed over the surface. And remember, these are very important applications because these are applicable for mass as well as for the charge. As I told you in first lecture, when you will study electricity, every approach will be the same, just instead of m you will have q, charge. Okay, so complete the booklet CCD02, and I hope you have watched the lecture CCD01 and completed the workbook CCD01. Now complete the booklet CCD02, then you can proceed for the third lecture. Okay.